natural log. It's a quite interesting function for the application in calculus, okay? So we are going to do the 4.4 and eventually 4.5 together, okay, to get this function and be able to continue getting to the second part of the course. Okay, so let's refreshing your memory, reviewing first the definition of these functions and whatever we need. We just do the review as much as we need for this course, okay? So what is going to be the natural log function? Different way to define it. We can do it in calculus. You can wait and do it in calculus too. Sometimes we do it using the idea of the calculus, but we can do it using the idea of algebra. Do it or no. This is the way we are going to do it. Okay, so that's it. If b is going to be the base, again, we have to assume it's a positive. If b is going to be a positive number, okay, it's a positive number, again, with the condition that b is not 1. Okay, if this is going to be the case, then we're going to define the log function. Then the, okay, logarithmic function, logarithm, with the base b or at base b, with base b is going to be denoted, okay, denoted by, the notation is going to be log of x at base b, y equal to log of x at base b, or with base b. So this is going to be the notation, and it's going to be defined, and is going to be defined in terms of the exponential function, because we do know everything about the exponential function. And it's defined, okay, by, it's kind of inverse of the exponential function. You see y equal to the log of x at b. We can write this one in other version. The version is going to be x is equal to the base b to the y. So this is exponential function, and this is the log function. For the first one, you solve for y. If you're given a function and you'll be able to solve for x, this new one is going to be called the inverse of the old one. So they are going to be inverse of each other, if you are familiar and using this idea from algebra. Otherwise, it's not important. Because whatever we need, we are going to explain it. Okay, so anything you want to do here, you have to go to the other side. We already know quite a lot about the other side, so that will help us. Now, regarding this type of the notation that we're going to use, there are a couple of them that are going to be important in calculus, so we are going to focus on those. One of them is going to be if this base b, if b happen to be equal to 10, okay, the resultant log in algebra, we call it the common log. If this is going to be the case, then, okay, log of x at base 10 is going to be called, okay, this is called the common log, the common, okay, that's it, logarithmic function. Okay, function. And we have a special notation for this one. It's going to be denoted by, okay, is denoted by, we write the log of x with base 10, we simply write the log x. So if you see the log x, you must realize that the base is going to be equal to the 10. Okay, so this definition of this new one, so you can have this function y equal to the log x. But if you want to do anything about it, so you have to reverse it into the exponential function. So in the case of the exponential function, you must know that This is going to be x equal to the base. The base is 10. 10 to the y. Okay, 10 to the y. It's, it's just a popular one to write it down. Question? Now, the one that we're going to use in calculus, and in a minute, I'm going to tell you why. The one that we're going to introduce in calculus is the one that connects us to remember, the natural exponential function. The natural exponential function is where the base is e. So if the base is going to be e, that irrational number, 2.7 something. If this is going to be the case, then you are going to have the log of x at base e. This is going to be called natural log. So this is going to be called, okay, we call it the natural log function. The natural, okay, logarithmic function. Okay, the notation that we're going to use is this one. It is denoted by, okay, it's going to be denoted by, if you have the log of x with base e, be denoted by ln of x, natural log. Okay, ln of x, which is the natural log. And we are going to use this one in this course in calculus. Let me show you how we can connect if you get anything else. Okay, so if you have y equal to the ln x, and if you want to do anything about it, you go to the other side. The other side means x equal to the base. The base is e to the y. Okay, so make sure to know this connection. We're going to focus on this one. And there is a relationship between these two for calculus. We show you that you don't need to worry about anything else. Okay, so y equal to the ln x, if and only if x is going to be equal to the e to the y. So I'm going to focus on the definition of all the properties I discussed about the natural log over here. Okay, any question? Now, let's see some property of this ln x, okay, that we needed. So we are going to check some properties. Okay, some properties of this function, y equal to the ln x. The first and most important part is the domain. What is the domain of this function? The domain of the function is x. So you check to see when x is coming from, or where x is coming from. X is coming from here. So the x is in fact in the range of the e function. You see, e to the something, that would be x. But remember, the e is a positive number. So whatever you do, this is positive. So this means this x must be positive. Okay, so the domain of the ln function is positive numbers only. And it's very important. We're going to use it in several places. So make sure you make a note, okay? So domain of the ln x means the possible values for x. X, where is this x coming from? X is coming from here. X is equal to the e to the something. E is 2.7. So this expression, whatever y is not important. This x is going to be always positive. Okay, so the domain of the ln function is going to be positive, 0 and positive infinity. So ln of 0 does not exist, it's undefined, or ln of any negative number is not defined. Okay, you can define the ln of a negative number using complex numbers, but they do it in physics, not in this course. Okay, so that would be the domain of the function. Any question? Now the range of this function, y. So where is the y is coming from? Y is here. Y is the exponent. And we talk about it. We can have any exponent we like. So the range of this function, is going to be all real numbers. Negative infinity and positive infinity. Okay, so this basically means if you think about any number, that number would be ln of something. Okay, that number would be ln of that something. Okay, so that's the domain and the range. Any question? Now, there are some properties of the ln that you use in algebra and in calculus. A couple of places we are going to use it. Okay, in future. So I'm going to repeat it. Those rules probably you have seen it in algebra. So the second property is going to be okay. Just to remind you that if you want to work with the ln function, you have to use your calculator. This is going to be your calculator. We needed a couple of application problem. So this is the notion of the ln that we're going to use. So if you want to find, for example, what is going to be, this is going to be ln. Okay, so let me just turn it on. You see, you click over here, it's going to be ln. Okay, so suppose you want to find what is going to be ln of 2. Then you click on 2. So close the parentheses, equal to. So that gives you 0.69. Okay, so any number, anything you want to find, this is the way we are going to do it. We talk about it. If you want to do something with the exponential function, you have to click on the second. Then the same thing, same place, ln. Okay, that's going to be 1. So it's going to be e to the something. So if you want to find, for example, e to the 12, you close the parentheses, and that gives you the big number here. Okay, so we need a couple of places we are going to use. We are going to find the maximum or the minimum of the given number. So make sure you know the case of the ln. Some of the numbers like ln1 is popular. You know that ln is equal to the 0. That's the ln of 1. And for the rest, it doesn't matter. You can use your calculator. So make sure you are ready for it, and you need a calculator for the next test. Because there are a couple of application problems that we have to give you one of them from the next section. Okay, so make sure you are ready for it. We don't need any other ln, and I'm going to show you in a minute why this is going to be the case. Okay, so that's going to be domain and the range of the function. That is going to be 1. Why the range is all real numbers? This is it. The range is y. Where is y coming from? From the exponent. Exponent of exponential function can be any number. So it's all real numbers. And we already talked about the domain of the exponential function is all real numbers. In the case of the ln function, you switch. The domain would be range, and the range would be the domain. You know, you've seen this type of things in algebra, but you can get it from these definitions. Okay, x coming from the result of the e. Result of the e is always positive. Y, where's the y coming from? Top. The top can be any number. Remember, we checked it the other night. So the other property that there are a couple of problems in your book that you have to use this one. Remember, we have something we call it power rules in ln. If you have any power, you can bring it down. They call it power rule in ln x. If you have a product, ln of x1, x2, they call it product rule. So they write it down as ln of x1 plus ln of x2. Okay, so the power rule, the product rule, and they have something they call it quotient rule. The quotient rule would be ln of, if you have the x1 over x2, it's going to be changed into a difference. Ln of x1 minus ln of x2. Sometimes, because we are going to differentiate, when you want to differentiate, if the function is going to be complicated, this property would be helpful, okay, in general. So we just remind you that we may use it. Okay, so that's going to be the power rule. We bring the n down, we shrink it in case of the ln function. If you have any product, you can change it to the sum. If you have any quotient, you can change it to into the difference if you like to get these numbers down. Okay, any question? Now, these are algebra. So what's calculus? The calculus, as usual, you know that we are interested in derivative of this function. Okay, so let's see how we're going to find derivative of the y equal to the ln x. Again, if we don't know anything over here, we go on this. Yes, what's the question?
Sorry, I just got a little confused. By looking at the equation above, how do we know that the range is going to be all real numbers?
What is the range? The range of the function is the value that you can assign to the y.
Oh.
Where is the y coming from? Exponent. Exponent, we already talked about it. Remember the other night?
Mhm.
Y can be a positive number, can be a negative number, can be a fraction, positive fraction, irrational numbers. So that's why it's all real numbers.
Oh, okay. Thank you.
Because you can use your calculator. That's it.
Oh.
If you want to find this exponent, if I give you any number, you know,
Mhm.
you just find it. Since you can find it for any number, so the range is going to be all real numbers.
Okay.
Okay?
Yes, thank you.
Okay. Now, getting to most important part of our argument is the derivative of this function. So how are we going to find the y prime? Again, in order to find the derivative, we cannot do anything here. Of course, we can do it, there are different methods to do it. But this method that I give you is a very short one. So in order to find the y prime, we cannot do anything over here. So we go here. So we go here, differentiate it. We just show you in the second page, in the next page. So number 3, the property 3, and this is the one that we are interested in, the only one. So this is going to be our argument that we say that the note that if y is equal to the ln x, then we change it. If we switch it, that give you what? We switch it to get the x equal to e to the y. Now differentiate both sides. Differentiate. Okay, differentiate. Of course, we differentiate with respect to the x. If you differentiate the x, derivative of x is 1. Equal to derivative of e to the y. Remember, derivative of e to the y, derivative of the e function is the e function. But you have to pay for it, remember? When it's anything other than the x, it's implicit differentiation. Remember implicit differentiation? Anytime we differentiate with respect to the y, we multiply by y prime. See? Derivative of the e function is the e function times the derivative of the y, which is y prime. So we were looking for y prime, solve for y prime. If you want to solve for y prime would be equal to, you get 1 over e to the y. But what is e to the y? E to the y is x. So that gives you 1 over x. So y prime would be 1 over x. That's it. Excellent proof. We have several proofs, but this one is the most easiest one.
Can you take that bowl out for me?
Okay, so that's going to be the one that we are going to have. Okay, so what we did, we proved that. Okay, so therefore, what we did, we proved that derivative of ln x is simply 1 over x. See? So I repeat it again, it's y equal to the ln x. You want to differentiate, you want to find y prime. We go to the other side, exponential part. We differentiate respect to the x, derivative of x is 1. Derivative of the e function is the e function, but it's implicit differentiation. You have to multiply by u prime or y prime here. So we solve for y prime, we divide by e to the y, but e to the y is x. So y prime would be 1 over x. So derivative of ln x is 1 over x. That's why this is popular in calculus, because of its derivative. Okay, but in general, sometimes you may like to find derivative of ln of anything else. This is x, so you can make it better. Make it better and to say that if u, as usual, equal to u of x is a differentiable function, okay, if this is going to be differentiable, then we have something much better. What is that? If you want to find the ln derivative of ln u, you see now you have to apply the chain rule because it's a two function. The outside function is the ln function. The inside function is u. Remember the chain rule? Equal to derivative of the outside, derivative of ln. Derivative of ln is 1 over, you see, 1 over u. That's the derivative of the ln. But times what? Times derivative of the u prime, which is equal to u prime u. So derivative of ln u, derivative of ln u would be what? Would be u prime u. Very easy again, derivative. So two formulas, 1, 2. So if you just want to find the derivative of ln x, it's simply 1 over x, you're done. But if it's something else, ln of x cubed plus 2x, for example. So you are going to call it u in that case, and we say this is the chain rule version. The chain rule version of the formula that give you u prime u. Okay, it's very popular and used quite a lot in calculus, the ln function. Okay, and now we can give you a first problem. If we give you two functions, you get one question in your next test by finding the derivative of the following function. Okay, so you have to memorize these two formula. These two, nothing else. I'll give you an example to see how we're going to operate. Example, we want to find the derivative of each function. Derivative of each function. Each function. The first one, we call it ordinary function. I gave a test at university and I gave them this one last week. So the first function is f of x equal to 5x cubed plus 2 ln x minus 7e to the x plus 12. So you want to find derivative of this function. So we differentiate, we go forward, one by one. See, solution using various rules that we have. F prime of x equal to, the first one, use the power rule. Okay, 3 times 5, 15. 15x squared, done. That's the first one. The next one is 2 times ln x. So derivative would be 2 times derivative of ln x plus 2 times derivative of ln x, derivative of ln x, 1 over x. So it's going to be 2 times 1 over x. Okay, that's 1. Next one, minus 7 times e to the x is going to be minus 7 times the derivative of e to the x, which is simply e to the x. Remember, e function is the e function. And derivative of 12 is 0. Cannot simplify it, but this is the way you write it down. F prime of x equal to 15x squared. And this would be 2 over x minus 7 e to the x. That would be the derivative of the function. Any question? So that's very mild one. No product rule, no chain rule. Okay, you need a basic definition. Okay, basic differentiation to differentiate it to get these numbers. Okay, we differentiate as usual. We get to ln x derivatives of 1 over x, and we get to the exponential function. It's going to be just exponential function. Okay, that's type 1. Question. Type 2. Type 2 is going to be the one that you have to use the product rule. Okay, and the popular one is this one. So that gives f of x equal to, it's going to be just a power of x times the ln x. Okay, so something like 5x to the 4th times ln of x. Okay, you want to differentiate this one. So this is a product of two functions because of the x for the first one. So the first function is 5x to the 4. The second function is ln x. You see, you just remind yourself that you have to use the product rule, f times s. So remind yourself that what is the product rule? See, product rule, derivative of the first times second, second first. So derivative of the first one would be f prime times the second one, s, plus derivative of the second one times the first one. Derivative of a second derivative of s would be s prime times the first one, which is going to be f. Okay, we're just reminding you that what is going to be the formula involved. Now we can go for it. Are you ready? Solution. F prime of x. Derivative of the first one, 5x to the 4th. It's easy. We apply the power rule, 4 times 5, 20. We reduce the power by 1 unit, so that gives us 20x cubed. So that would be 20x cubed for the first one. Okay, this derivative of the first times second times what? Times ln x. This is second. Okay, now plus the derivative of a second times first. Now the second one is ln x. Derivative of ln x, we talk about it, 1 over x. So that gives 1 over x. Times it by the first one. The first one, 5x to the 4. You see, this is a situation we're going to have. So derivative of the first is just 20x cubed. X to the, yes, x cubed times ln x. Second first, derivative of ln x is 1 over x. When you are not done, you get the chance to simplify this one. You can think about this one as 5x to the 4th over 1. Now that gives you the chance to simplify it. Always it's possible to simplify. So 1x would be out, and that gives you 5x to the 3rd. So the final answer is going to be this one. F prime of x is equal to 20x cubed ln x, and over here is simply 5x to the 3rd, and then be done. You see, very nice method in order to get it, and very popular. And you can't do anything else. Some people try to do something, they try to factor 5x cubed. No, why you factor it 5x cubed? This is going to be the end of the problem. Okay, so it's going to be a product rule, derivative of the first times second, second first. Derivative of the first one is just the power rule, 4 times 5, 20, 20x to the 3rd, times the second function, which is going to be ln x, plus derivative of the second times the first one. Derivative of the ln x, 1 over x, you have to know this one, times the first one, 5x to the 4, but you always get the chance to simplify. So we simplify one of the x out, and then there you are. You get the derivative of this function. Okay, what's the question? To get the numbers is going to be no, ln x is not equal to 1 over x. Derivative of ln x is, this is it. Derivative of ln x is 1 over x. Okay, derivative of the first times second, second first. Derivative of the first, 20x cubed times the second, plus derivative of a second times first. Derivative of ln x, 1 over x. Okay, so that's going to be type 2. Any question? So that would mean different things, different powers, x to the 3rd, x cubed. There are a couple of application problems, so that you are going to have this type of numbers involved. Okay, any question? So there is no need for the chain rule so far. Now we're going to get to the next one, which we need chain rule. So what's going to be the next one? Number 3. Number 3, look at this function. f of x equal to ln of, okay, ln of x to the fourth, okay, plus 5x squared. So that's going to be, that's going to be the next case that we are going to have. Now, look at this one. It's not ln x, it's ln of something else. So you may call the inside something like u. You see this one? You may think about it, that's going to be ln u. So you realize that you are going to differentiate ln u. So you have to use the chain rule version of the derivative of the ln function. The chain rule version, as we talk about it, is what? Is u prime u. So we have to use this formula, okay, because it's not x. So simply the solution is going to be f prime of x equal to, get a quotient, on the top derivative of the inside derivative, which is easy, power rule, 4x cubed, okay, 4x cubed plus 2 times 5, 10, 10x, that's your u prime, divided by u, which is x to the fourth plus 5x squared, and you're done. You see, very easy derivative. U prime. I've seen some people, they made a mess for this one. They try to simplify it. You don't supposed to. Sometimes you may get the chance to simplify it, but it's not your job. You just you want to find the derivative of the function, and that's u prime u. U prime u. There is no ln. When you do it to get this number. Any question? So that's going to be the chain rule type. You have some problems in your book that you can use that algebra that I talk about it. Look at this one. This is going to be, suppose you have g of x equal to the, let's say, ln of the cube root, okay, ln of the cube root, and you have the x squared minus 1. You see this one? This is again of the form of the ln u, the u prime u. You can do it if you want, but you can use some algebra to simplify this one. Especially, you know that you don't like the radicals. So you switch the radical first, as you do it as usual, okay? So the best thing to do for this function is this one. So you have your g of x. So this is going to be ln. So switch that into the x squared minus 1 to the third. Okay, now remember I talked about that algebra part that you're going to have. Okay, the algebra was the power rule in algebra. The power rule is that if you have any power, you can bring it down for the ln function. We shrink it. So this g of x would be equal to the 1/3 ln of x squared minus 1, you see? So we rewrite it. We rewrite it now. Is much easier to differentiate rather than the original one. Of course, it's not possible for all the functions. This is very a special one. So we remind you that in case you get a chance to using this type of property, it's okay. You can go ahead and use this type of ideas. So and now the derivative is going to be g prime of x is equal to, you keep the 1/3 as is, and this is ln u. See ln u, u prime u. U prime derivative of x squared minus 1 is going to be 2x, and the u is x squared minus 1. So you can rewrite it as g prime of x equal to, the top would be the 2x, the bottom one you multiply by 3. So that gives you 3 times x squared minus 1. So that would be the derivative of the function. Okay, so these are the most that you can go for to finding the derivative of the function. Any question? So derivative of ln x, 1/x, okay, and derivative of ln u, u prime u. that give you the result right away. Now, we can ask question. Previously, when a function was given to, remember, we could use solve some optimization problems, finding the maximum and the minimum. It's going to be the case for this one too. Okay, there are a couple of, you got to be careful when you want to introduce a function because of this ln function, but you have a couple of nice one and usually give you one. Okay, so that is the derivative you done. Okay, so let's have one. Let me just tell you something about derivative that we are not going to do. You may wonder why we just use ln function, but I introduced other log for you. You see, you have the log at any different bases that you're going to have. So the reason is that in algebra, we have something that we call it, you can convert, if you like, is any other log function. So let's just do a remark. You know, there are a couple of just in your assignment. You are not going to use it, and we are not going to give you anything other than the natural log. But in case you know it's happened and you want to use it, this is it. Okay, we remark that from algebra, if you be given any other log, you see if you be given log of x with base b, you can switch it. You can write it down as ln x divided by ln b. See, ln x is your function. ln b is a number. Depends in this base. If the base is going to be 2, 3, 5, whatever it is, you can find it. So when you find that this is, you can rewrite this one as well, as 1 over ln b, then ln x. It's just algebra. You see, you get, you know, if you get a half, if you get a 2, it's going to be 1/2, 1/5. Okay, 1/5 ln of x. So that makes things easy for us. What does it mean? This means if you want to find the derivative of this function, so you have to find the derivative of this one. But 1 over ln b is a number. You just find the derivative of ln x, which is 1 over x. So the log, that's the reason that we use the ln function. So the derivative is going to be 1 over ln b as is, but this would be 1 over x. Okay, or if you like, you can write it as a 1 over x ln b. So this is going to be derivative of this new function. But we don't usually memorize this type of formula because we don't like to carry on this ln b all the time. That's why we just use the base. Our base is just a natural log. So the derivative simply would be 1 over x. You don't have to carry these numbers. But if you have it, or you know, as is in your book, then you are not going to worry about it. So I just give you one. So look at this one. If y is equal to the log of, okay, so if this is going to be log of something like, let's say 3x minus 2 at base 5. If you want to differentiate it, so if you want to differentiate it, change it first. You see, then we change it first, change it to what? Y equal to, the top would be ln of 3x minus 2. The bottom one would be what? ln of 5. So quickly I change it into the ln function. I can pull out the 1 over ln fifth, or even, you know, I can get the number even. You see, look at this one, but they are messy when you want to do it. You see? So this is going to be your function. So if you want to differentiate it, go ahead, differentiate it. Y prime 1 over ln 5 stay as is. For the rest, u prime u. u prime, derivative of the inside 3, u, 3x, okay, 3x minus 2. So that would be derivative of the function. Because of this ln5, ln2, ln3 is not popular to apply it. Okay, so that's the reason that in calculus, you go with the ln x all the time. Because ln x is easy to handle. Okay, you don't have these. Because later on, you want to let it equal to the 0, find the maximum, the minimum. Then you have to carry these, ln5, ln2, ln3 all the time. But it may happen, in application problems. So that's why we are going to just remind you the possibility. But I will give you only the natural log, the example that I talked about. Okay, any question? Now let's do one problem. For example, we want to find the maximum and the minimum of a function, and we may have a ln involved. These problems cannot be complicated because they have to give you something easy, because you may not be able to solve the resulted equation. So they're going to be of this format. This is similar to one in your book, and then you have it in your next practice one, a couple of them. So this is the last thing that we need from the ln function. Okay, so what is the problem? The problem is, would like you to find. Okay, find a relative extrema, maximum or a minimum. Relative extrema of this function. What is the function? The function is f of x equal to what? X squared over 2, 1/2 of the x squared minus ln x. It's very similar. It's one of the example of your book, probably. Just I want to explain it because it's very important case. And we have a couple of them similar to this one, so that you will see similar one in your next practice one. Okay, so there you are. We have a function. We want to find out what is going to be the local or relative maximum or relative minimum of this function. We just do it as we did it before. Remember, you have to go with the domain first. Domain first. Some of you missed the domain on the test. Solution. Any suggestion? What's the domain of this function? X squared is clear. This is all real numbers, but we have the ln function. When we have the ln function, no, not all real numbers. No. Remember, we talked about the ln function. What was the domain of the ln function? We talk about it that the ln function, the domain is going to be all, yes, Peter Parker, you're right. The domain of the ln function, positive numbers only. You see, positive numbers only. It's very important to get the domain. So the domain of this function is positive numbers. Remember, you cannot define the ln of 0, or you cannot define ln of any negative number. That's the domain. Now, as usual, differentiate it. Let it equal to the 0. To get the critical numbers, go back, plug in the critical numbers into the function, and then test it. What type of test? We have the first derivative and the second one. You have to decide which one are going to use. Okay, so this is going to be the procedure for finding the relative maximum and the minimum. So differentiate. To differentiate it, this is it. F prime of x is going to be equal to 2 is just a constant. So the derivative of x squared is going to be 2x over 2 minus the derivative of ln function, which is 1 over x. Okay, the derivative of x squared is 2x. Now 2 and 2 would cancel out. So this would be what? This would be x minus 1 over x. That is going to be the f prime. Okay, so the f prime of x is equal to the x minus 1 over x. Any question? That's the f prime. Let it equal to the 0 to get the critical numbers. F prime of x equal to the 0. So you have x minus 1 over x equal to the 0. You have to solve this equation. We already done similar one. You have to get rid of the denominator. So you have two choices. One choice is multiply by x both sides to remove the denominator. The other choice is when it's two terms only, move one of them to the other side, use cross multiplication. Okay, so you can use either one. So I do usually the cross multiplication one. So I move the 1x to the other side. That's 1x. Now I can cross multiply. X would be x squared. I get the x squared equal to 1. So I take the square root. X would be positive negative 1. Okay, so there seems to be both of them are going to be critical numbers, but not. What is the domain? Domain is positive numbers. So you have to drop the negative 1. Okay, so x equal to 1 is fine. Is in the domain, but x equal to negative 1 is not. So we have only one critical number. Critical number is going to be 1. Any question? So this is the way, as I told you, this is going to be very mild equation because you cannot put any ln you like because you may not be able to control the result, which is going to be this equation. Okay, so in that case, in this case, it was possible. So what you're going to do, you have to go back and drop the 1 into the equation, then test it. So it's going to be f of 1 into the function. That is the function. Replace the x by 1. So that gives you 1/2 minus ln 1. And then 1 is 0. You can check it with your calculator if you don't believe it. Okay, so this is going to be 0. So f of 1 is equal to the half. This is the candidate. Is it a maximum? Is it a minimum? You have to test it to get the numbers. Okay, so ln 1, you just check your calculator to get the result. Okay, so this is going to be the case. So ln 1 is 0. So f of 1 would be 1/2. Any question? Now you have to test it. Is it a minimum or is it a maximum? Okay, so testing. You have two choices. First derivative test or the second derivative test. Remember, you see, look at your f prime. This is your f prime. If you want to do the second derivative test, you have to find the second derivative, you know that. You find the second derivative and you check the concavity at x equal to 1. If you want to use the first derivative test, you have to draw a table and check the sign of the f prime. Okay, you can begin. I'm going to do the second one for this one. Okay, but you can do also the first. Second derivative test. So for second derivative test, I have to differentiate again. So what I have the f of x equal to the x minus 1 over x. I'm going to rewrite it. I write it at x to the negative 1, make it easier to differentiate. So that's f prime. So now I differentiate it again to get the f double prime. F double prime, derivative of x is 1. And this would be negative 1, negative positive. 1 down, x to the negative 2. Okay, we just differentiate it, just using the power rule. Now I'm going to reverse this one into the positive, I flip it. So that gives it a 1. Okay, so f double prime of x is 1 plus 1 over x squared. Officially, you have to drop the 1, but it's already positive. It's positive. F double prime, remember, it's concavity. Positive means up. So you get a minimum. Okay, so f of 1 equal to the 1/2 is in fact absolute minimum. You can say relative, it doesn't matter. because it's a minimum, and this is the only minimum. You don't have anything else. You have only one critical number. If you have only one critical number and you get the minimum, this must be absolute minimum. But relative or absolute for this one would be the same. So f of 1 equal to 1/2 is the absolute. That's better, absolute minimum. So this is how we're going to test these, okay, these type of problems, if you like. The other one is very similar to this version, so that you'll be able to solve, take care of that equation, the result of the equation nicely. Otherwise, sometimes it's getting complicated. Okay, so this is going to be the way we are going to operate it to get these natural log function. Any question? So the takeaway from this section is going to be the derivative. The derivative of ln x is 1 over x. In the chain rule type, you find the derivative of ln u. The derivative of ln u would be u prime u. That's all you need. Then for the, any other type of the log, you are not going to worry about it because the things getting complicated when you go through those type of numbers. Okay, but you have an introduction type in your book that they talk about it. That's it. That's it section. Okay, that's section 4.5. Finding the derivative of the function. Now, there is a kind of application in 4.6. It's going to be exponential growth and decay. I'm going to give you an example on that one. That would be good for your test. You probably, it from algebra, but in algebra, they didn't prove it for you. So I give you a break now. We come back and I take care of that section for you. So be done with the ln function. You don't need anything else. That's 4.5. I'll give you, just a couple of examples on 4.6, and then that's done. Then you can do probably next time. We can start chapter 5 for the rest of the course. Okay, so it's 8:10, 10 minutes. Then we come back and we finish. Okay, I'm going to give you some idea of these application problems in 4.6, the last section of this chapter. Okay, is a 4.6. Now it's mostly application in that can be used in biology or social science, and if you are measuring business, in business also it can be used. But we just give you just a couple of them, just in case to see the application of these type of ideas. And if you have a similar one, then you won't be surprised. Okay, but there are very nice, nice cases for these functions. So what we are going to do, so this is 4.6. We give you one question or one or two in your next test. Okay, 4.6, the idea is we call it exponentially growth. Okay, exponential growth and decay. Okay, decay model. This is it. You see, if you like, if you open up an account and put the money, the bank would give you some interest. So over the years, your investment will grow, it's getting bigger and bigger. This is going to be the case. The other one's going to be decayed using chemistry over the years. The substances, they will lose their masses, and this is going to be the decay. Or if you just order a pizza, the pizza getting cold, so the temperature going down, if you like. So this is two different formats that we're going to have. Now we want to create a formula for this type of problems. You see, in everyday life, most of the time, if you have a situation like investing the money in the bank, so your rate of change, you know that the rate of change is the derivative. Now you know it. So the situation is going to be the rate of change in your investment depends on how much are you going to invest to start with. If you invest more money, so you are going to get more interest, if you like. So we say that the rate of change of your investment is going to be proportional to the function. So for example, if you get rate of change of the population, we say 2%, 5%. 5% of what? 5% of the total population. Or when we say that the unemployment rate is 2%, 2% of what? 2% of the full population of the country. So all these cases that we are going to have in everyday life is going to be the case that the rate of change is proportional to the amount. We want to know from calculus point of view, what does it mean, this result? Can you find a model for it? Okay, or coronavirus. The growth of the coronavirus is exponentially, it is exponentially growth. Okay, the growth is exponential, or exponential growth means it's fast and big. So can we find a formula to predict what would happen for the next 6 months? Yes, these are going to be the case of this, okay, of this section. So I'm going to introduce the mathematical model parts, okay, then we try it with a couple of examples. So that's the idea. You see, so this is going to be the case. If you have a function, the function is going to be a function of time. So if y of t, okay, if y of t is going to be a differentiable function, is the amount, if you like, is a differentiable, okay, if it's going to be a differentiable function, of time, okay, of time, if you like, t, such that, as I talk about it, the rate of change would be y prime, is proportional to the amount. Proportional to the amount means it's going to be a fraction of the amount. So it's going to be something like k times y of t. You see, k times y of t for some, okay, for some a constant k, constant k. Okay, so unemployment rate, 2% of the full population. This is going to be the one. The interest in your investment, 2%. 2% of what? Of whatever you start with. So it's going to be always the case. Now, we want to know what sort of function can we have? What sort of function would satisfy this condition? That the derivative of the function is going to be just a multiple of the function, if you like. You see, and note that, can you give us a function whose derivative is the same as the function? Any suggestion? Of course, other than zero function, because derivative of zero is zero. A function whose derivative is the same as the function. Do you know such a function? What is derivative of e to the x? You see, the e function, derivative of exponential function is the same as the exponential function. So note that derivative of e to the t is just e to the t. So this is y prime of t, this is y of t. So I give you a function whose derivative is the same as the function. Can you think about a function whose derivative is twice of the function? Any suggestion? Finding a function whose derivative is 2 times the function. No? What is derivative of e to the 2t? Remember the chain rule? You have to use the chain rule because of the 2t. Derivative of the e function is again the e function, but you have to pay for it. Derivative of the top 2. So it's going to be 2 e to the, okay, e to the 2t. That's going to be a function whose derivative is twice of the function. You can go on forever. You see, if you want to find a function, you see, look at this one. Derivative of a k, derivative of the e to the kt, a derivative of the e function would be just e to the k times your prime, which is the k. So that would be k e to the kt. So that gives you an idea. What type of function would satisfy this condition? That function is going to be of this format. Okay, so this will tell you that. You know, it can be proved in more details in calculus 1, 2, 3, but that would be fine. So therefore, if y prime of t is equal to the k yt, then we can argue that we have this y of t for you. Y of t is going to be of this format, e to the kt. But you know that if you have it twice, 3 times, 4 times, that would be the same. The formula that we are going to suggest is this, the way we write it down, c, a constant, times e to the kt. So any situation that we have that satisfies this condition, unemployment, coronavirus, investing the money in the bank, this would be the formula. This formula gives you the amount anytime you like. Y of t equal to the c e to the kt. What is going to be this c? You see, in order to find the c, you can replace the t by 0. So e to the 0 would be 1. That gives c equal to the y of 0. So this is going to be where c equal to the y of 0 is going to be the initial value. The money that you start with is the initial value of the function y. So basically, this would be our model. Y of t. Your book stay with the c, but I'm changing it. So y of t would be y of 0 e to the kt. You see, this is going to be the machine, mathematical machine that satisfies all those conditions that we have. So if the rate of change is proportional to the function, depends of the rate 2%, 5%, whatever it is, the function must be of this form. And this k, that rate is going to be called, k is called the proportionality. Proportionality constant. So the k would be proportionality constant, y of 0 the initial value. When you start putting money in the bank, you may start with $1,000. So y of 0 is $1,000. Okay, $1,000 and the rate of the 2%. So quickly you can have a calculator if you like. You get this calculator and then you can find your money in the bank anytime you like. If this k happen to be positive, your money getting bigger and bigger and bigger. So in this case, we say that we have exponentially growth. If this k happen to be negative, your money getting a smaller and smaller amount. So in that case, it's going to be, we call it a decayed form. So that's why we call it exponentially growth and the decayed problem. So we explain it that if k is positive, exponential, okay, it's going to be positive exponential growth. Okay, growth occurs. And if k is negative, if k is going to be negative, then exponential decay occurs. So this is the case that we have. You see, when you come to the room from outside, you say it's cool. So when you say it's cool, it's exponentially cool. The reason is this formula. We just change it a little bit. The difference between your body temperature and the temperature of the room, y of t, is going down exponentially. So in that case, k is negative. That's why you feel, you feel that it's cool. Order a pizza. When you order a pizza, it's getting cold exponentially. So in that case, again, you have, you have these decade, if you like, that you're going to have. So investment of the money, growth of the bacteria, they are all going to be in this form. Okay, so we just use the calculus to prove it. The rest are going to be algebra, like the one that you did before, probably in your algebra course. So a situation would be created. You are going to put this model. So in order to get the model, you have to find the k for each problem. The k would be different. And the initial value, then they usually ask two questions. They give you one value for the t. They say, what would happen to my money after 5 years? So you replace the t by 5 using your calculator to get the money. And the other one is, we say, how long? We say, how long does it take for the investment to get to the $100,000? So this means y of t is 100,000, you have to find the t. So it's going to be only the two cases that you have. You talk about rate of change, you already got the rate of change, which is the y prime. Okay, so basically this is the idea of this exponential growth and decay. Of course, there are various forms of this problem. In this case, we assume that the growth is going on forever. But if it's going to be growth of the population, you have to modify the formula, because you cannot let the population get bigger and bigger every day, because you don't have the facilities. Okay, you don't have enough rooms, jobs, so you have to put some restrictions. So they changed the formula a little bit. So it's quite a lot of interesting case. Okay, so I'm going to give you just one or two examples, one for the decade and one for the growth, to see how we're going to operate with this formula. Okay, and then we are done with this section. Okay, the first example is something like the everyday life. Okay, some kind of bacteria. Okay, these are the example that I use in calculus course, calculus 1, 2, 3, but we can have it with yours too. And we put a couple of them in your, this is too easy, okay? It's not bad, but everything is given to you. But the one that you are going to do for us, you have a little bit more job to do, okay? I'll let you know. So what is this? This is it. When, okay, when the E. coli, this is a name of the bacteria. Okay, bacteria, I have to explain the problem. Okay, when this is going to be grown in the lab. Okay, grown in the lab. What would happen? It increases. It increases. Okay, increases exponentially. Exponentially. Increases exponentially with a growth constant. With a growth constant. Okay, with the growth constant of k equal to, k is given to is 0.41, okay, per hour. So that's the rate of the growth, if you like. So what do you want? Assume that, okay, assume that you start with the 1,000 bacteria. 1,000 bacteria are present, okay, are going to be present at t equal to 0. So this basically means, okay, this means i.e. y of 0 is 1,000. That's the initial values, if you like, okay, it's going to be initial values. So assume that 1,000 bacteria are present at t equal to 0. So what they like you to do is going to be the following. So the first thing, they ask you to give us a model for this one. Okay, find the formula. Find the formula for the number of the bacteria, for the number of bacteria, which is y of t, at time t. This is simply just write the formula. I do it, one step by step. I just go on. Okay, so this means the k is already given to you. See, this is your k. Your k is 0.41. Initial number of the bacteria are 1,000. Okay, so what you would like to do, you would like to have the formula for y of t. So we just give you the formula, you just substitute. You see the formula is what? Is y of t equal to the y of 0 e to the kt. Now substitute. If you substitute y of t is equal to the what? Is equal to the 1,000 e to the, okay, k, which is the 0.41 t. So this is going to be your model. Okay, you have to tell us the measurements for t. Remember, it was in hours. So you have to mention that t is going to be in hours. Okay, so y of t is going to be what? Y of t is the number of. So this is the number of. Okay, this is going to be number of the bacteria. Number of the bacteria at the time t, after time t, at time t, which is in hours. Okay, that's it. That's the first step that you have to assign it yourself or just find it yourself. K is positive, so it's going to be the growth. Then they ask you two questions as I talk about it. They give you a number for the time. They ask for the number of the bacteria. And they give you the number of the bacteria and ask for the other one. Okay, so this is going to be part B. Part B, they ask how large. Okay, how large is the population? How large is the population after 5 hours? After 5 hours. You have the model. This is your calculator. You want to know what will happen after 5 hours? Then you replace the t by 5 and find y of 5, which is going to be number of the bacteria. Okay, so the solution of this part is going to be simply your t is equal to the 5. So you would like to find what is y of 5. You go to the model and substitute. So it's going to be y of 5 is equal to 1000 e to the 0.41 t 0.41 times 5. Then you have to use your calculator to get these numbers. Okay, so this is how we are going to do it with the calculator. So I need the e function. So that's going to be the one. I click on the second and on the L, put on it on first. See, that's on. So the second I go for the ln that give me exponential function. So I need 0.41 times it by 5 times it by 5. So this is the e. Then I multiply by 1000. Okay, times it by 1000. So that will give you the number 7,767.9. Since they are a number of the bacteria, okay, then you have to run that. So the y of t, y of 5 after 5 hours, this is the number of the bacteria that we are going to have. 7,000, okay. So this is it, that give you 7,767.9. We run it to the next whole number, 7,768. So this is going to be number of the bacteria after 5 hours. That's why they are dangerous. See, you start with the 1000, and after 5 hours, you get 7,768 of those. Okay, so this is going to be part B, how large? Okay, so there's going to be a part C. Any question? It's all algebra, really. The calculus is just setting up the function. Otherwise, it's all algebra. So what is going to be C? C, how long? How long does it take for the population to get somewhere? So they ask you when. Okay, when will the population, reach, okay, reach 10,000? Okay, so this means you do have the y of t, which is 10,000, then you have to find the t. See how long t is missing? T is missing, and the number that you have is y of t. So your y of t is going to be 10,000. So you have to go to your model again. You see, this is it. You go back to this model, replace the y by 10,000, then you have to solve for t to get these numbers, okay? So going back to the whatever we have. So this is the one we have, the model, y of t is equal to the 1000 e to the 0.41 t. So we are going to replace the y of t by 10,000. So 10,000 equal to 1000 e to the 0.41 t. You have to solve for t. Okay, you have to solve for t. That's the point. Solve for t. The way we do it, we have to solve for the exponential part first, then you bring it down. So we divide by 1000, so e to the 0.41 t would be, it's going to be 10,000 divided by 1000. So the result would be 10. Okay. So what we have is e to the 0.41 t is equal to the 10. Now, if you want to solve for t, you have to bring the t down. The only way that you can bring it down, it takes the ln of both sides. Then, you see, it's going to be ln of e to the 0.41 t equal to the ln of 10. Now we can bring the 0.41 t down, and the ln e would be just 1, would disappear. Okay, so we continue. Any question? So bring the 0.41 t down. So that give you, this is it, it's going to be 0.41 t ln of e, okay, is equal to the ln of 10. Ln of e is 1, so we can ignore it all the time. So what we have is 0.41 of t times t, if you like, equal to the ln of 10. So t is going to be equal to the ln 10 divided by 0.41. This is how we solve for t. Okay, any question? Then you have to go to your calculator again. Getting ln of 10, this is it. I turn it on. Then I need the ln, this is it, ln of 10. That is going to be 10. Okay, it's going to be ln of 10 divided by, this is it, divided by 0.41. If you divide, that give you the, that give you the number. Is a point, did I miss anything over here? No, that was ln 10 over, so let's, that's 0.01, just 0.1. I made a mistake over there. Okay, so I repeat it again. It's going to be ln of 10, ln of 10. Okay, that's it. Now I divided by is 0.41. 41. 0.41, that gives you 5.6 in hours. Okay, so t would be, t is equal to the 5.6 of hours. So you have to wait something like, 5.6 hours to get the, to get the population from 1,000 initially to the 10,000 to get that, to get that growth, if you like. So this is going to be a situation that you have. As I told you, the fun part is just the proof from that part of the calculus that you're going to have. And you have, a couple of examples in your book. We just want to make sure that you are able to do it. Okay, I give you one for the decade. You have a table in your book, they want to talk about it. When we get to the decade, we are going to have these substances from chemistry. In the case of those substances, we have something that we call it half-life. So the half-life is going to be, when it grows, we have something we call it doubling time. So doubling time means the time that takes for the y of t to grow to its double of the original one, if you like. So if you invest money, put in $1,000, so doubling time would be the time it takes for the 1,000 to double up to get to the 2,000. You know, they talk about the unemployment rate. So unemployment is going to be double up in 4 years. So that would be for the growth. For the decade is the other way around. You lose substances, okay? So the half-life is going to be the time it takes for the original one to change to the half. So I give you the formula for the half-life. It's not difficult to prove. It can be proved easily. Then you can solve the problem of the problem of a decade. Then we are done. We are not going to spend more time on this. So this remark is going to be, okay. So I call it half-life formula. Half-life formula. You need this one to be able to solve any problem for the decade. So, so for the half-life, this is the way we do it. This is T of H. This is going to be half-life time. It's going to be equal to the ln of 1/2 half-life divided by that K. Remember the rate that we talked about it. Ln of 1/2, you know that 1/2 can be written as 2 to the negative 1. So this would be the same as, or is going to be negative ln of 2. Because the 1/2 is 2 to the negative 1, and you can bring the power down in the case of the ln function. So it's going to be divided by K. So this would be the half-life formula. But in the problems that we're going to have, there is a table for the chemistry. They do know the half-life of all the substances. So what we are going to use this formula is we take the half-life and we use it to find the K. So I'm going to switch it and you memorize this formula. K is going to be equal to negative ln2 divided by the half-life. This is the key for any of those problems. So the half-life would be given. So the T of H is the half-life. Because it's already measured. Okay, it's already measured. You know, they use it in order when they find out a fossil, you know, a dinosaur, and they check and they tell you that, oh, the age of the dinosaur is something like, you know, 1 million years, etc. The way they do it, exactly, they use these formulas that we're going to talk about it. Because they check the around that, okay, that materials, if you like, they have something that they call it, okay, I think it's volcanic rock, if you like. Or the volcanic rock, you know, it's kind of potassium. So they do have the half-life of the potassium. So they get the K, they put this modeling that we are going to have, and then they find out. And they tell you what's going to be, you know, what's going to be the life. So with the growths, we predict the future. With the decade, we study the past. This is the way, you know, they describe it. Okay, so for this new problem, the second one, you have to know this formula. And we usually give you one of these because it's easier. And then we just give you the example. The example that I have is, you have quite a lot in your book. They like this type of example more than the other one. So I should give you this example. I picked one of those chemical one. I think it is plutonium. That is going to be the case. Yes, I'm going to explain it. I'm going to have to write it down. One of these substances, okay? So one example of the decade is usually easier than the one. Okay, so there you are. We are going to start with let me just give you the problem. There's a story about this problem. So suppose 10 grams. Okay, suppose 10 grams of plutonium, which is very dangerous. 10 grams of plutonium. Okay, plutonium isotope. Isotope, suggest the name PU 239. Okay, was released. You know, there was a nuclear plant in former Soviet Union in a place that I think today is in Ukraine. So there was a factory over there, if you like, or the plant. So there was a link of those nuclear material in Chernobyl. I think it was around 1976 or somewhere. So it was in news all the time. So this problem is related to that event. Okay, so suppose 10 grams of plutonium isotope Pu-239 was released. Okay, released in the Chernobyl. That was the name of the place. Okay, Chernobyl is going to be on. This is YL. Chernobyl nuclear plant. I think it's in Ukraine today. Nuclear accident. Okay, so we start with the 10 grams. This is going to be initial value. Now you see, it has half-life. It has a half-life of quite a lot, 24,100 years. Okay, this is it. So that was the situation. Now, what do you want to know? We want to give us a model for this problem. Okay, so part one. Part one, the question is going to be how much. This is the formula. How much of the 10 grams? Okay, how much of the initial one, 10 grams, will remain in T years. Okay, like the previous problem, we need the model first. To get this part, you see the initial value that you start with is 10 grams. Okay, that's the initial value. You have to find the K first. You have to find the K because your formula, you know the formula. Your formula again is y of t equal to the y of 0 e to the kt. So you need to find that. You need to find the K. In order to get the K, we use the half-life in this problem right away. So the half-life is given to you is 24,100 years. So you are going to use the formula that I talked about it, K equal to negative ln2 divided by the half-life. Okay, so this is going to be equal to the negative ln2. The half-life that we have is what is 24,100. So you have to use calculator to get this number. Okay, so and there you are. I have the ln2 is easy. It's just 0.69. You don't need. We can check it. It's going to be ln. Okay, that's it. ln2. Okay, ln2, and this is 0.69. You divide it by 24,100. So the result is this one. It's almost 0. But remember, you are not going to round these type of numbers too much, if you like. Okay. So you just, when you round it, you at least keep a couple of decimal places. Okay. So this is it. is going to be a negative number because it's a decade, and you get quite a lot. Sometimes they write it down in scientific form, scientific numbers, we don't mind. So I have 4 zeros, 1, 2, 3, 4. Then I have a 28761. If you want to run that, you have to have at least something like, 3 decimal, 3 non-zero number after those 0 zeros. But it's just application of the calculator. So it's not going to be a big deal. Okay, so this is going to be the K. So your model is going to be Y of T equal to, initially we have 10 grams, it's going to be 10 grams, e to the K, this is K, negative 0.0000. I have a 28761 T. I just bring all of them, but you can run that if you like. Okay, this is going to be our model. You have to explain the T. The T is going to be in years. Okay, so this is going to be amount of the leftover, if you like. This is going to be in grams. What is going to be left after, okay, after T years for the first part. Okay, so for the first part, actually they ask for the model, for the formula. Any question? Now then they ask 2 questions, again, like the one that we did. So the next part is they want to know how much of the 10 grams will remain in 1,000 years. So this means you replace the T by 1,000 to get it. So part B, how much will remain of the 10 grams? Okay, will remain. You want to know what will happen after 1,000 years? Years. So simply you go back and you substitute. You get the T equal to the 1,000 to get the numbers. Okay. What's the question? Yes.
I'm sorry, do you mind saying again how you got the negative ln2 for the K?
It's a formula.
Oh, okay.
That's the one.
Oh, yeah, I see it.
Yeah, because that was ln1 half. I didn't prove it. So
Oh, okay.
it would be this algebra.
Got it,
So
thank you.
it's but you have to know it. Make a note. It's a negative ln2, not positive. Because if you put a positive, situation would be gross. If it's a negative, it's going to be decay. Okay, so it's a formula. So let's see what we want. How much of the 10 grams that remain after 1,000 years? So we are going to check. We replace the T by 1,000, okay, to get this number. So what is going to be Y of the 1,000? Again, your calculator. It's going to be 10 e to the negative 0.000028761. I just bring all of them times 1,000. You have to use your calculator to get this one. Okay, and this is how we are going to do it. We need the exponential part, so I go with the second and open up click the ln, that give me exponential one. So I have a negative number, so I start with a negative sign here, and then my number is going to be 0.1234. Then I bring, I check all of them, 28761 times it by 1,000 times it by 1,000. So that would be equal. This is it. This is the number. Then I have to multiply by 10. Multiply by 10. So that would be the result. 9.7. You see? That's why they are dangerous. You start with the 10 grams. After 1,000 years, it's almost the same. It's a 9.7. Okay, so this is going to be equal to the 9.71 grams. Okay, so Y of 1,000 is going to be equal to the 9.77 grams. Okay, so this is going to be the second part. Any question? Now, you may be interested to see when this would disappear, if you like. So that's the next part. The next part, they say how long it will take for the 10 grams, okay, to be decayed into the 1 gram. Okay, so see, after 1,000 years, didn't get anywhere. So it must be quite a long one. Okay, any question? Let's do the last part. The last part is going to be how long will it take to get into the 1 grams? Okay, so this is the part C. The part C, how long? We make it shorter when it's on the test. Just one of these. How long will it take for the 10 gram? For the 10 grams to be reduced of the sample. To decay, okay, to decay to 1 gram. 1 gram. Okay, so this means you have to go back to your formula, and you have to replace the y of t by 1. Y of t by 1, and then you solve for t to give us how long. Okay, going back to the formula that we have. If you put the y of t equal to the 1, so this is going to be a situation that you have. It's going to be 1 equal to what? Equal to the 10 grams that we did have, e to the negative 0.123428761 t. You have to solve for t. So we solve for the exponential part first, divide by 10, e to the negative 0.000286761 t is going to be equal to the 110. You can write down the 0.1 if you like. Okay, we take the ln of both sides to bring that t down. So it's going to be ln of e to the 0.000286761 t, and this would be ln of a 0.1. Remember, bring that the power down, and the leftover is going to be 1. So it's going to be negative 0.1234286761 t, which is equal to the ln of 0.1. So eventually your t would be ln of 0.1 divided by negative 0.1234286761. ln of a number less than 1 is negative, so this negative would be positive. You must be careful, okay, because the time cannot be negative. So we go back again. We need the ln of 0.1. 0.1. That's the ln of 0.1. Then I want to divide it by what? Divided by a negative. It's going to be 0.1234. And then we have the 28761. So that's it. The number, a big one. Let's see. 8,059 years. That's what it takes to disappear to the 1 gram. Okay, so it's going to be t equal to is going to be equal to the 80,059 years. 59 years. That is what would takes for the 10 grams to reduce to the 1 gram. Okay, that's why they are very dangerous to get these numbers. Okay, so that's it. I just sometimes I don't teach this section to your discipline, the calculus for business, but we just wanted to see make sure that you are able to apply your application, your calculator, because we give you one question, we may give you the model. We just give you the model, which is a little bit different, and we ask you to do this type of idea for us. And when we get to your review, you are going to have the one that you are going to use the derivative as well. Because if we ask for the rate of the growths, then you have to differentiate it. So that is the purpose of these sections. That's it. We are done with chapter 4 and we are done with the first part of the course. So in the first part, a function was given to you, you find the derivative of the function. So for the rest of the course, we are going to do it the other way around. A derivative of the function would be given, you have to recover the function. So the first operation was called differentiation, and you get the derivative of the function. This new one is called anti-differentiation or anti-derivative. Then we have another name for it, we call it integral. So we check this chapter 5 for you. In chapter 5, the first two sections is the machine that we need. So we have to make sure that we get these two sections first. So we spend something like a week to talk about these two sections. Then the rest is going to be just theorems, definitions, but the crucial one is 5.1 and 5.2. And most of the problem from the final, it comes from that section. So you better pay attention. I'll just let you know when we get to it. Okay, so we do it next time on Tuesday. 5.1 antiderivative and the 5.2 integration by substitution method. That's it. Any question? So just have a look. Don't worry about it. You know, it's study the derivative of exponential function and the log function. We don't need anything else. You must know that the derivative of e to the x is e to the x. The derivative of e to the u is e to the u times u prime. For the ln function, the derivative of ln x is 1 over x. The derivative of ln u is u prime u. This is all we need from chapter 4 when we get to the rest of the course. Okay, so nothing to worry about. So, okay, have a good night and see you next week. I'll finish your quiz, I post it, and then the solution, then we can talk about it. Bye-bye.